Welcome to the introduction to the second law of thermodynamics. Here we'll introduce the second law and talk about how the second law leads to the introduction of a concept called entropy. So first, I'd like to recommend referring to the roadmap section of the resource section at the back of the Atkins book. In the 9th edition of the Atkins book, it's on page 911. And I recommend referring to that multiple times throughout this chapter. It should help quite a bit to provide a succinct view of the relationships between the principal equations in the chapter. So first, let's introduce the concept of a spontaneous change and a non-spontaneous change. So with a spontaneous change, this is the direction of change that does not require any work to bring it about. So if we have, let's say, some gas in a vacuum and or in a container, and then so we have some gas molecules in our container, and if we have another container next to that and then we remove this wall in between the two, what do we expect to happen? Well, we expect these molecules, some of them, to move over into that other container, into the vacuum. And we expect that to happen spontaneously. We don't expect to have to do any work for that to happen. And of course, the reason for this is that as we make the container larger, the gas molecules, because they're constantly moving around, will occupy that extra space. There's nothing keeping them out anymore once we remove that wall. So this is a spontaneous change. It doesn't require any work to bring that about. Another example is the cooling of a hot object to the temperature of the surroundings. So if you put a bowl of hot soup out in your kitchen and just leave it for a while, it will eventually cool to the temperature of the surroundings. Now the surroundings, the air around the bowl of soup, will eventually heat up slightly as it gains that energy. Another example is combustion of hydrogen and oxygen. If we burn hydrogen in air or in oxygen, that process is spontaneous. It will continue once we've initiated the process with a spark. I'd like to point out here that spontaneity, whether or not a process is spontaneous, doesn't imply that the process occurs quickly. It even doesn't imply that the process actually occurs at all. The process could be limited kinetically, which we'll get to later in the course. Is only saying which direction the process would go if it goes anywhere. So the opposite of a spontaneous process is a non-spontaneous process. So a non-spontaneous process is the direction of change that requires work to bring it about. So this is the exact opposite. So if we have here our case of our gas, if we remove that wall and we've allowed our container to expand, essentially, the gas expands to fill up the entire container. If we want to go back and get all of those gas molecules back from the right side back onto the left, we're going to have to do some work. We're going to have to move those gas molecules. And so this is a non-spontaneous process. We're going to have to put in energy to get this process to occur. So this is something like the compression of a gas, the heating of an object above the temperature of its surroundings. We have to put in energy to get that to happen. The electrolysis of water to split the hydrogen and oxygen back apart again after we've burned it. We need to put in energy, right? So in a spontaneous process, you don't always get energy out, but in a non-spontaneous process, you always have to put energy in to get that process to happen. Now, you don't necessarily have to be putting energy into the system, but you have to be using up energy somewhere, either in the system or the surroundings, to get that to happen. So this introduces us to the concept of the second law of thermodynamics. The second law of thermodynamics says that no process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. So if we look here we have a hot source. So we have some source of energy, some source of heat, and we transfer some heat from that hot source into our heat engine, right? And that's symbolized by this yellow circle here. We use some amount of that energy, and we get some amount of energy out as in the form of work. And what the second law of thermodynamics is saying is that we can't get all of this QH, the heat that leaves the hot source, we can't convert all of that into work. There has to be some amount of energy, some amount of heat that goes into a cold sink. Another way of saying this is no heat engine can be 100% efficient. We can't convert all of that heat from the hot source into work. Some of it has to go into the cold sink. Right? So, in other words, we can't have a heat engine without a cold sink. We've got to have some heat leaving the hot source, some heat going into the cold sink, and some portion of that heat that leaves the hot source can be used to do some work. So another example of this is that a ball sitting on a surface doesn't just spontaneously jump up from the surface. So if we have some surface and we have some ball sitting on the surface, if we observe that ball over a period of time, the molecules in that ball are moving around randomly, the molecules in the surface are moving around randomly, but the molecules in the surface and the molecules in the ball, in order for the molecules in the ball to all move the same direction, that's what it would take for the ball to move off the surface. For the ball to jump up spontaneously off the surface, all the molecules in that ball have to have an upward kinetic energy component, right? Some upward motion to it. And that's just not going to happen randomly. It may happen with a single molecule or with a small collection of molecules, but with something on the macro scale, like a ball, there are way too many molecules, it's just not going to happen randomly. Also, if that did happen, that if all of the random motion of the molecules in the surface did happen to align to do work on the ball, and the ball then leaves the surface, what this means is that kinetic energy is leaving that surface and being transferred to the ball. That would mean that the surface would be cooled off in that process. And that's a non-spontaneous process. So, what makes a process spontaneous? We can't say that the energy of a system tends towards lower values, although it's tempting to say that, because in our example where we had the expansion of the gas into a vacuum, that gas isn't changing its internal energy, and we saw this in the last chapter, chapter 2. So we can't say that the energy of a system tends towards lower values, because that doesn't always work. It's not always true for a spontaneous process. Furthermore, if the internal energy of a system decreases during some change, then the first law of thermodynamics requires that the energy of the surroundings increase by the same amount, and thus the internal energy of the universe is constant. So we can't say that it has something to do with energy. Spontaneity isn't directly tied to energy, because the internal energy of the universe is constant because of the first law, and that means that from the universe's perspective, if our system is the universe, there is no change in internal energy. So if that's the driving force for a process to be spontaneous, we can't have any spontaneous processes in the universe. So a spontaneous process always changes the distribution of energy within a system or within the universe in such a way so as to disperse that energy. So with our example of the gas molecules in a container, and then we expand that container or remove a wall. As the gas expands, there's some amount of kinetic energy associated with each molecule. Beforehand, they're all on one side in one part of the container. Afterwards, they're spread out. So we're dispersing that kinetic energy in space. And so that's a spontaneous process. So spontaneous processes always increase the dispersal of energy, whether it's in the system or in the surroundings or in the universe as a whole. All right, so let's go back to our example of a bouncing ball. Right? So as we have a ball and it bounces on the floor. So the ball is our system. Right? So this is our system here, the ball. And as it bounces on the floor, we're saying the floor is the surroundings here. The ball bounces and some amount of energy gets transferred, some of that kinetic energy gets transferred from the ball, the molecules in the ball, into the molecules of the floor. Right? So that's symbolized by these arrows here. And every time the ball bounces, it's losing some kinetic energy to the molecules in the floor. And that means that it bounces up a lower and lower height each time until eventually it doesn't rise off the surface at all. It just stays on the floor and doesn't move anymore. And so what has to be happening here is that as that kinetic energy is leaving the ball and going into the floor, those molecules in the floor, those molecules, as they're moving away from the ball, they're heating up. So the floor is heating up. It's a small amount because there's not a whole lot of energy in that ball compared to the thermal mass of the floor. But the floor is heating up. And so if you drop a whole bunch of balls over and over and over again on a floor, it will eventually get hot. Okay, so on the other hand, if we have a ball that's resting on our warm floor, right, in order for that ball to suddenly jump off the floor, the random kinetic energy, so each of these molecules or atoms in the surface of our floor, as they vibrate back and forth, they're hitting that ball. And if enough of them vibrate in the right way, if they all go up and transfer enough kinetic energy to the molecules in the ball can jump up off the floor. But the molecules in the ball all have to be moving the same direction. If they're moving different directions, like in the left case, then the ball just heats up. Right? So it doesn't help us really to heat up the molecules in the floor. We don't expect the ball to suddenly jump up off the floor, because as we heat up the floor, those molecules transfer some of that kinetic energy to the ball, and those molecules in the ball, as they start moving faster and faster, they're not always moving straight up. They're moving left and right, they're moving sideways, diagonally, forwards and backwards. They're all moving different directions. And so in order to get the whole ball as a whole to move off, all of those molecules have to be moving upwards, like this. And that just doesn't happen. Statistically, it's unlikely. Now, this type of localization of random disorderly motion, the heat, as concerted ordered motion is so unlikely for any macroscopic object that we dismiss it as virtually impossible. We say it just doesn't happen. Now, that's not true on the microscale, right? So this effect that is impossible is only true on the macroscale. It is in fact observed on the microscale with a single atom or molecule, or with small collections. So if you have something like a mote of dust, we do see this, and it's called Brownian motion. We can observe this in the movement of dust particles suspended on the surface of water, let's say. Those particles are bouncing around. And if we look in a microscope, we see those particles moving back and forth as the water molecules collide into the dust particles and give them some kinetic energy, and that kinetic energy gets transferred back and forth. All right, so this brings us now to the idea of entropy. So where the first law of thermodynamics leads to the introduction of the concept of internal energy, U, the second law leads to the introduction of entropy. So remember that the first law identified permissible changes, possible changes in the universe. The second law identifies from amongst those possible changes, from amongst those permissible changes, the spontaneous changes, the changes that occur without a driving force, without any energy being put into that process. So entropy is symbolized with the letter S, a big capital S. And this is a measure of the energy dispersed in some process. So if the entropy change for some process is positive, the energy is being dispersed, that's going to be a spontaneous process. If the energy dispersal is negative, if the energy is getting more concentrated in a location or with some object, that's a negative change in entropy. That's a non-spontaneous process, and that process won't occur without some driving force inputting energy into that process. All right. So we can also express the second law as the entropy of an isolated system increases in the course of a spontaneous change. And so we can label that this way with a change in the total entropy is greater than zero, where this delta S total is the total entropy of the system and its surroundings. So if we have down here, we have some system, some generic system with a boundary between it and the surroundings. What we mean here is the entropy of the system plus the entropy of the surroundings, which really we mean the entropy of the universe. So in any spontaneous change, the entropy of the universe must increase. If the entropy of the universe doesn't increase, the change is not spontaneous. If the entropy change of the universe is negative, that means that the process is non-spontaneous. That process will not occur. We have to put in energy to get that to occur. Okay, so thermodynamically irreversible processes are spontaneous processes, and thus they have to increase the total entropy. Right? So the total entropy of a spontaneous process must increase. The total entropy of the universe must increase. Okay. So our definition of entropy focuses on the change in entropy, ds, that occurs for some process. A change in the extent to which heat is dispersed depends on how much energy is transferred as heat. So remember that heat stimulates random motion in the surroundings. If we transfer heat from the system to the surroundings, there will be an increase in entropy of the surroundings. Remember that work stimulates ordered motion of the surroundings, and thus it's not increasing the entropy. It's not increasing the disorder of the surroundings. Only heat being transferred from the system to the surroundings will increase the disorder of the surroundings. So the thermodynamic definition of entropy is based on this equation, ds equals dq reversible over T. So Q reversible is the reversible heat being supplied. Okay. So for some measurable change, now we have delta S instead of ds. We integrate this from some initial state I to some final state F. And remember that dq is an inexact differential, so it depends on the path taken. So in this case, because we're looking at the reversible heat, we have to find the reversible path between the initial state I and the final state F. Also note that if we're heating the system, then the temperature is different at each infinitesimal point along the integral, so T is changing there. Alright, so let us examine the infinitesimal transfer of heat, dq surroundings, SUR, from the system to the surroundings. So the surroundings are a reservoir of constant volume. We're assuming that the volume of the universe isn't changing. So the energy supplied to the surroundings by heat is equal to the change in the internal energy, du. So that's this first equation here. Note that we could also regard the surroundings as a reservoir of constant pressure, in which case the energy supplied as heat is not equal to the internal energy, or the change in internal energy of the surroundings. It's equal to the change in enthalpy of the surroundings. So that's this equation, the DH equation. So recall that the internal energy U is a state function. So this du of the surroundings, the change in internal energy of the surroundings, is independent of the path taken. Right? So that means that in this equation, if the left side is independent of the path taken, that must mean that the right side is independent of the path taken. And therefore, that in our equation here, where we have ds is equal to dq over t, we can remove this reversible constraint. We no longer have to require that the path taken between the two states, the initial state and the final state, are reversible. It doesn't have to be reversible anymore. Also, the temperature of the surroundings is constant because it's the universe, and so, or the remainder of the universe. And so we now can say that delta S for the surroundings, the change in entropy of the surroundings, is equal to the heat transferred to the surroundings divided by the temperature of the surroundings. We no longer have to integrate. So, whether the change is brought about reversibly or irreversibly doesn't matter anymore when we're calculating the entropy change for the surroundings. It does matter for the system, but not for the surroundings. And for an adiabatic change, the surroundings absorb no heat. Therefore, the heat transferred to the surroundings must be zero. So for an adiabatic change, the entropy change of the surroundings has to be equal to zero. This expression here is true so long as no local hotspots are formed in the surroundings. That is, as long as the surroundings remain in internal equilibrium. If one part of the surroundings are hotter than another, then this equation doesn't work. Note that if hotspots do form, then the localized energy in that hotspot can disperse spontaneously and will disperse spontaneously, which would generate additional entropy. Right. So, in addition to the thermodynamic view of entropy, we can also examine a statistical view of entropy. So, remember that an atom or molecule can possess only certain values of energy, right? So we have some energy states, and at some temperature we have some population of states that are occupied. That is a horrible curve. As we go up in energy, fewer and fewer molecules are in those states, and as we're at lower energy, more molecules are in those states. If we increase the temperature, then more and more molecules are at the higher states within have higher energy states. All right, so the continuous thermal agitation of molecules that aren't at absolute zero, so at T greater than 0, ensures that their energies are distributed over the available energy levels. So we have this Boltzmann distribution. Now, Boltzmann proposed that the entropy of a system is linked to these energy levels, and here we get the Boltzmann formula for entropy. So this is this S equals K natural log of W, where K is the Boltzmann distribution. Sorry, not the Boltzmann distribution, the Boltzmann constant here. And W, this capital W, is the number of microstates, the ways in which the molecules of a system can be arranged while keeping the total energy constant. Note that each microstate lasts only for an instant and corresponds to a certain distribution of molecules over the available energy levels. And then in the next instant, those molecules, once they've collided, they're in a different distribution of molecules over the energy levels. So, because of this Boltzmann formula, as the number of microstates available to a system increases, that means that the entropy must increase. As W increases, S increases. And thus, if we have more microstates available to the system, the entropy is higher. Also note that if we have only one microstate, then W is 1. And so here we have then the entropy is equal to K times the natural log of 1. Natural log of 1 is 0, so K times 0 is 0, which means that the entropy of a system with only one microstate is 0. That makes sense. If there's only one state available, then there's no disorder in the state. We know exactly which state the system is in. If there is only one microstate, the system always has to be in that state. There's no disorder at all. There's no uncertainty where what the system looks like. As long as W is greater than 1, then S is greater than 0. So as long as the number of microstates is greater than 1, then the entropy of the system is non-zero. There's some positive amount of entropy around. And as the number of microstates increases, as W increases, the number of ways to achieve the same energy increases. So our entropy is increasing. We have more ways of rearranging our molecules. So let's examine a collection of gas molecules in some container. So here we have some container that is initially some volume. As we expand that container from here, from this wide to this wide, a wider container, the energy levels become closer together. We saw this in the quantum mechanics part. And so the total energy, remember, the total internal energy of a system of our gas molecules undergoing expansion into a vacuum doesn't change. So if the total energy stays the same, but now our microstates are closer together, that means more microstates are available. So as our gas is expanding into a larger volume, the entropy is increasing because we have more microstates. So this explains why the gas explains why the gas expands into the larger volume. Okay, so now let's examine a system of molecules at high temperature. Right? So we have our Boltzmann distribution here with some number of states. at high temperature, the populations in the higher energy microstates is still fairly significant compared to the population in the lower energy states. And so an increase in the temperature doesn't change the relative populations of the high and low energy states, microstates. And so an increase in entropy should be small as we increase the temperature a little bit when it's high. On the other hand, if we have a low temperature, so over here we had high temperature. And here we're having low temperature. So at low temperature, the microstates are the same distance apart. But now, at low temperature, we have lower energy, and so the decay of our populations is much faster. And so these low energy states have a much higher population of, or fraction of the molecules in them than at the higher energy states. And so as we increase the temperature a little bit at low temperature, we're appreciably increasing the number of microstates available. And so the increase in entropy should be large because we're opening up some of these higher energy states. So for a change in entropy, the change in entropy should be inversely proportional to the temperature, right? And that's where we're going to stop for now.